Welcome to Auto 155 Electricity and Electronics 1. My name is Tony DeBlasi, and in this lecture I will be covering wiring schematics and circuit testing. This is part 2 of a two-part lecture based on Chapter 45 from the Automotive Technology Principles, Diagnosis, and Service, 6th edition. For additional information on this topic, please read this chapter and refer to the PowerPoint found in the course content folder. Please note that there are both audio and visual lecture attendance codes scattered throughout this lecture. Please write these codes down as you see and hear them. At the completion of this lecture, you will be required to go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture. We will begin this lecture by marking up this wiring schematic with the appropriate colors based on the voltages in their current states. This schematic represents the horn diagram from a Toyota Tacoma pickup. What I like to do is start from my always hot or my always ground sides. So I'm going to begin with the power side. At this point, I've gone as far as I can go with my always hot or voltage at all times red marker line. What I will do next is I will mark my grounds. At this point, I've gone as far as I can with marking my ground side. If you notice down at the horn switch, this is a ground side switch associated with a clock spring. I know that when that switch is closed, it will give the circuit ground. So I will mark that with a yellow. I've gone as far as I can with marking my ground side switched circuit in the yellow. The last color I can use would be my blue color. And my blue color is anything after a switch on the positive side. Now that I have the circuit marked up accordingly, I can test at different points to see if I have good powers and good grounds. If I were to take a test light and test for power at terminal number 1 at this relay, I should have voltage. It should light up. If I did not, then I would probably want to check this fuse here. Using that same approach, I could test for other points along the way to see if they had power. If everything was working properly, then I could switch my test light to ground checking mode by attaching the alligator clip to battery positive, and then I could check for good grounds. Now that I know from my diagram where those grounds are, I can make quick work of this diagnostic process. The next component that we're going to cover is a relay. Relays are probably fundamentally one of the most important, critical system components that we will cover in this course. A relay is a magnetic switch that uses a movable armature to control a high amperage circuit by using a low amperage electrical switch. So in other words, we can have a high ohms, low amp solution to control a high amperage circuit. This cuts back on running heavy duty wire everywhere. This cuts back on excess heat. It can actually allow us a lot more control. And in today's vehicles, relays are commonplace. They're everywhere. So we have to first understand how they work so that we can understand how a circuit fails or has a fault. When you can identify the relay that controls a component, you can actually come in and cut that circuit's diagnostic time in half. We'll begin by talking about the pinout, in other words, the terminal identification. The first ones that we're going to focus on are the International Organization for Standardization, or ISO relays. These are very, very common. They use terminals 85, 86, 30, 87, and sometimes 87A. There are relays with the exact same pins, and sometimes they're called something differently. For example, Toyota likes to use 1, 2, 3, and 5. We'll get into that a little bit later. It really helps if you understand what these terminals do, so that way you can understand how to test it. So the coil inside that creates the magnetism, those two terminals are 85 and 86. The load side of the relay, which is the switch side of the relay, are terminals 30 and 87. 30 would be the input, 87 would be the output to the load. Now, it says 87A. Inside of this relay, we have a switch. Currently, that switch is resting up against 87A until we activate it. When we activate the switch, it moves from 87A to 87. So some relays actually have two throws inside. So an 87 is one circuit, and 87A is another circuit. Now, the thing we have to understand about relays is because there's a magnetic coil, anytime we energize a coil, it creates a magnetic field. When you turn that coil off, that magnetic field will dissipate. And when that magnetic field dissipates, it releases a blast of voltage. It's called a voltage spike, otherwise known as counter electromotive force, or CEMF. We have to have a way to control that. So we use things like diodes and resistors. So that's referred to as relay spike control. For a lot of people, relays can be a very difficult component to understand. They want to know, why is it there? Why is it complicating this circuit? Why can't we just tap off the original circuit? Hopefully this example that I present to you will help alleviate some confusion you might have. When I think of a relay, it can best be described as a load on one circuit and a switch or multiple switches on another circuit. They are a very common form of circuit control. They allow for a very small current with longer, thinner wire to control a higher current, shorter, thicker wire type circuit. So let's walk through the basics of how a relay is wired up. We start at the power source. We'll ground our power source, and I'm going to run a very teeny tiny thin wire to a switch. And you can see here in this example, I have two switches. I have a power side switch and I have a ground side switch. Both of these switches control a coil. That coil of wire, when we close both of these switches, allows current to flow through and it creates a magnet. That's all it does. When this coil magnetizes, it creates a magnetic field around it, lines of flux that travel from the North Pole to the South Pole, and any ferrous metal being metal that is easily manipulated by magnetism, it will close switches in its proximity. So the next thing I'm going to do is I'm going to run another circuit adjacent to this one. But this circuit is different. Instead of longer, thinner wire, this circuit has heavy-duty, thick cable, and it's running higher current because the load that it's powering is big and strong and it requires a lot of wattage, like a starter motor, for example. What you see in the center of the screen is essentially the relay, tucked away behind a plastic little box in a power distribution panel. Take note of the pinout. 86 is the power side of the coil, 85 is the ground side of the coil, pin 30 is the input to the heavy-duty switch, and then 87 is the output of that heavy-duty switch that carries the current off to the load. If we were to compare these components in this circuit example to something real, then the little tiny power side switch would be my key, and the ground side switch would be my park neutral safety switch. So when we turn the key over, we send power to the power side, 86, as long as the vehicle is in park or neutral. If the vehicle is in drive or reverse or any of the additional lower gears, this switch will remain open, preventing the relay from becoming a magnet. And this is in place for obvious safety reasons. We wouldn't want the vehicle to start while in gear. When these two switches are closed, that relay has close to 78 ohms in it, which is going to allow for 160 milliamps or 0.16 amps. Because of that, we can use little teeny tiny wires to actually control this relay. The other side of the relay, pins 30 and 87, are actually carrying current capable of running a starter. So this starter is running 1 to 300 amps. When current leaves the relay at pin 87 and goes to the starter, it's actually powering an additional relay, which is on the back side of the starter, which is called a solenoid, which we'll get into later on. It's allowing current to run into that solenoid. So what we have are multiple relays all working together to perform a function. Figure 45.25 is a top-down look at a relay, very similar to the last slide that I just showed you. You can see that it lists the pinout where the power side of the coil is 86, where the ground side of the coil is 85. You can also see the input being 30, resting on pin 87A now. When the relay is activated, because every schematic shows switches in the normal off position, so this is how the relay would be when it's not activated, it states that 87 is the normally open output, or NO output, while 87A is the normally closed output. So if we were to test this relay unplugged, laying on its back with its pins up, you could take a multimeter and test for continuity between pins 30 and 87A, and your multimeter would beep. You would have continuity. If you were to test from pins 30 to 87, it would not beep. However, if you were to put power and ground using a jumper wire to 86 and 85, you would get continuity at pins 30 and 87. In this slide, if you notice, it says most relay coils have between 60 and 100 ohms of resistance. Because we have such high resistance, we have such low amperage. Figure 45.26 is a cross-section view of a relay up close. So you can see your pins 86 and 85, which are your power and ground sides of the coil. Pin 30, as it comes into the relay, actually ends up not using a wire at all. It uses the chassis of the relay for its switching and connection. So it travels in from the pin 30, it goes up and over the lid, the movable armature is pulled down, and then contact is made between these 2 points so current can flow out to pin 87. Figure 45.27 shows a typical relay, and it also shows the relay socket. If you notice on the side of the relay, it actually gives you a little schematic. Many relays have that schematic on them. Many relays also don't have that schematic, but this is kind of nice because it shows you what the pins mean. Figure 45.28 re-explains what we talked about already, that all schematics are shown in their normal non-energized position. I say off, but non-energized position. In this relay, there are only 3 terminals. There's a 1, a 2, and a 3. 2 would be the input from the power side, like 86, the power side of the coil. 1 would be the ground side of the coil. And as you can see, down at the horn switch, this is what controls the coil. When that horn switch is closed, the coil is given ground. When it's given ground, it energizes, and it closes the switch and allows the horns to beep. Terminal 2 is also supplying power for what would normally be pin 30. So in this case, they're using a single terminal to be both the input for the power side of the coil and the input to the internal relay switch. An important thing to discuss is that when a coil is energized and it becomes a magnet, obviously it creates a magnetic field. More importantly, when we turn it off, there's an event that happens. Usually there's a breakdown of that magnetic field, which results in a voltage spike. In many cases, that voltage spike can backfeed into a circuit and damage it. In figure 45.30, this is showing a transistor that just switched off, removing the ground from the coil. In doing that, the coil's magnetism broke down, releasing a blast of counter-electromotive force. You'll notice there's what's called a clamping diode attached in parallel to the coil to prevent that CEMF, or that counter-electromotive force. In figure 45.31, instead of using a clamping diode, they used a resistor to absorb the voltage spike. Now that we have fully reviewed what the pins on the relay correspond to, we can now test the terminals inside of the relay socket. These socket terminals are only identifiable by matching up how the relay inserts into the socket. Many relays, with the exception of a few, have offset pins, making it so they only insert one way into the socket itself. Once you have referred to the wiring diagram and established which pins match up with the socket terminals, you can test the circuits based on what they should have for powers and grounds. This example is based on a correctly working and very common basic relay setup. The relay's pin 86 has a power side switch controlling when the coil is energized. Note there is no switch controlling the coil's ground side, pin 85. Other relay setups may have this control function. The circuit leg, which leads to pin 30, is fused, and pin 87 is the output to deliver current to the bulb. If we were to test this socket with a digital multimeter, we would start by checking for voltage at the 86 terminal. When we close the switch, we should see voltage on the meter. The battery voltage confirms that the coil is receiving power when the switch is activated. Now we can test for ground at terminal 85. There is ground voltage at terminal 85, which establishes the coil will have the necessary power and ground needed to control the switch that would normally exist between 30 and 87. Let's now test for voltage at terminal 30. Since there is voltage at terminal 30, this tells us that the fuse is good. and the terminal 30 has the necessary input voltage to operate the bulb. The last thing to check would be the output at pin 87. In order to do this, we need to set up our multimeter to read ohms and verify there is continuity from 87 through the bulb and then to ground. Since we see an ohms value on the screen, this shows us that there is continuity to the bulb, and that eliminates the possibility of an open on the output side of the bulb. Diagnosing relays takes a little bit of practice, and many can get a little bit more complicated. It's good to practice on good working relay setups so that you have a firm understanding on how they should work. As they get more complicated, just refer to the wiring diagrams to have a better understanding on how they are controlled. Chapter 45, Lecture Code Question Number 8. Please write this down. 62354. Once again, that's 62354. Please write this down. There is a tech tip that explains that by using a relay tapped into an existing circuit will help to prevent overloading that existing circuit. Relays typically have between 50 and 150 ohms in their coil resistance. This draws between 240 to 80 milliamperes of current when connected to a 12-volt source. If that's the case, then it will not overload the existing circuit. This works out really well if you're adding additional bulbs, if you're adding additional components, such as a winch or a sander or an air compressor or something else that would normally overload a circuit that you are splicing into. Now that we've covered how to interpret wiring diagrams and we've reviewed the function of a relay, what we're going to do now is go over some techniques for identifying circuit faults. The first one that we're going to cover is locating an open circuit. When it comes to locating an open circuit, the typical procedure would involve the steps that I'll go over in a second. But before we even begin these steps, the first thing that I do is I verify the complaint. I want to ensure that the problem with the component or system actually exists and it's not just a misunderstanding from the customer standpoint. I've had examples where a vehicle wouldn't start, but the customer just simply didn't press down hard enough on the clutch pedal, or there was a piece of carpet bunched up behind it. Once I verified the complaint, I learned that that was actually the problem and there was nothing wrong with the circuit to begin with. So after you've confirmed that, you want to perform a thorough visual inspection. Make sure that connectors are plugged in, make sure that wiring is intact. You're going to print out the wiring schematic. You're going to review the wiring diagram to understand how the system works. You're going to check everything that does and does not work. And then you're going to test for voltage. Check for either common powers and or common grounds on the circuit that you're evaluating. So when you're diagnosing an electrical problem that affects more than one component or system, refer to the schematic to look for common power sources or common grounds. If they're common, that's where your fault may be. Examples include underhood lights, inside lighted mirrors, dome lights, right and left side courtesy lights. In figure 45.32, this is a typical wiring diagram showing multiple switches and bulbs powered by one fuse. As you can see, this is the power and ground side of the circuit. We have one single fuse at the top, number 14. If that fuse were to blow, then all of these bulbs would go out. You can also see there is a common ground associated with this light switch. If that ground connection were to go, these bulbs would go out. So one example of a circuit troubleshooting procedure would be with regard to backup lights that are inoperative. First off, you verify the malfunction or verify the complaint. Then you would check for everything else that does not operate correctly. I would check the fuse for the backup lights. Then I would check for voltage at the backup light socket. One very effective method or procedure that I have found is the V1 through V4 method. You'll go into a lot more detail with this in the Electude module, Fault Finding Basics. The V1 through V4 method would be V1 is the battery voltage. You would check that to make sure there's adequate battery voltage. V2 would be checking for voltage at the load. V3 would be checking the ground side voltage drop. And then V4 would be checking the power side voltage drop. To give you a better understanding on the V1 through V4 method, we'll go over a couple of examples. In this example, we're displaying the V1 portion of the test, which tests for voltage at the power source. Confirming source voltage should be the first step in the V1 through V4 process. It does not matter if the load is on or off. In this example, we're displaying the V2 portion of the test, which tests for voltage at the load. In a functioning circuit, you should see the applied voltage, or maybe a tiny bit less to account for wire resistance. You should see this general voltage with or without the bulb in the socket. If the bulb is not working and you have voltage at the bulb, confirm that the socket and terminal contacts are clean and tight. If there's a good possibility that the bulb is bad, you can further test the bulb for continuity. You'll need to set your meter to ohms and place the leads onto the bulb's contacts. If the meter says OL, then you have confirmed that the bulb has an internal open element and needs to be replaced. If the element was good and actual ohms displayed on the meter, then check the contact positioning once again and verify there's no corrosion in the bulb socket itself. This is the V3 portion of the V1 through V4 method. In this example, we are measuring the voltage on the ground side, or in other words, ground voltage drop. In a working circuit with current flowing, we should see a very small amount of voltage on the meter. Disregard the negative symbol on the meter as it is just indicating the polarity of the meter leads. This tiny amount of voltage, 5 millivolts, represents the resistance in the wire and the chassis ground. If that voltage were to be too high for manufacturer's specifications, for example, 200 millivolts, then there might be an issue with unwanted resistance in the ground side feed wiring or connections. If we were to open the switch on the power side of the circuit, the meter should eventually show 0. This can also occur when there is a blown fuse. Notice the blown fuse and open switch have the same effect on the meter with regard to the 0 reading. Now let's replace the fuse and go over another scenario. With the switch closed and a good fuse, if we were to have an open on the ground side, the meter would display full voltage. If after doing this, you strongly suspect an open on the ground side, then open the switch on the power side. If you see an erratic ghost voltage displayed on the meter, you just confirm that there is an open on the ground side. This is the V4 portion of the V1 through V4 method. In this example, we are measuring the voltage on the power side. Just like in the V3 portion, in a working circuit with current flowing, we should see a very small amount of voltage on the meter. This tiny 13 millivolt amount represents the resistance in the wire. This is also called a voltage drop test. If that voltage were to be too high for manufacturer's specifications, for example, 500 millivolts or 0.5 volts, then there might be an issue with unwanted resistance in the power side feed wiring, and it would look like this. By removing this corrosion, we can restore the circuit back to its acceptable voltage drop of 13 millivolts. If we were to open the switch on the power side, we should expect to see full voltage on the meter. With the switch closed, if the fuse were blown, the meter would also show full voltage. As in the example with V3, if we were to have an open on the ground side and an open on the power side, we would see ghost voltage on the meter. In figure 45.34, it suggests to always check the simple things first, and I totally agree with this. Check the fuses for the circuit you're testing. If they're blown, that would indicate that there was some kind of high amperage event. High amperage events usually mean a short circuit. When it comes to locating a short, there are many different ways to do this. It can be difficult, but after you've done a few, they start to follow a pattern. The definition of a short circuit is when an electrical connection on the power side comes in contact with a component on the ground side, completely skipping the load. When it skips the load, it skips the engineered resistance for the circuit, causing an increase for the current threshold in that circuit, which then causes the fuse to blow. There's many ways of trying to find a short circuit. There's the fuse replacement method, where you would disconnect one component at a time and then replace the fuse. This is not the preferred method because you go through a lot of fuses. There's the circuit breaker method, where instead of using a fuse, you would use a circuit breaker. So every time the circuit breaker trips, the short circuit is still in play. When the circuit breaker stops tripping, you just found where the short was. There's the test light method, which is the one that I typically tend to use and I will demonstrate, where you remove the blown fuse from the holder and you connect the test light in the output side of the fuse. The test light will light up when there is an active short, and once you found where the short is, the test light should go out. The buzzer method is very much like the test light in that it makes a buzzing sound instead of showing a light, and the buzzer will keep buzzing until you found where the short was. When you remove the short, the buzzer should stop buzzing. And then there's the ohm meter method, which is very similar to the test light and the buzzer method, but instead of a light and instead of a buzzer sound, you'll see continuity on the meter. When you finally find the short and remove it, then the meter should say OL. There's also a Gauss method where you're going to use a circuit breaker at the same time, and just before the circuit breaker trips, you'll actually pick up the magnetic field on the Gauss gauge, and eventually when you stop picking up the magnetic field, you found the location of the short. There's also what's referred to as a circuit tracer method, or I call it the tone generator. So you put in a device to generate a tone out through the wiring as a transmitter, and then you have a handheld receiver where it'll create a tone as long as there is current flowing through the wire creating the short. You can follow that tone until you find where the short is. So I'd like to provide an example on how to use the test light method for finding a short circuit. Currently, this circuit is working perfectly fine. We have our power source, we have our conductive path, and we have our two light bulbs connected in parallel. We also have a fuse, a switch, and a connector. Then, all of a sudden, the lights switch off and the fuse pops. The circuit has an active short. The copper in the power side wiring is somewhere touching ground. That's a power side directly connected to the ground side. Every time a fresh fuse is installed, it pops again. The first thing to do is remove the fuse. This provides us a place to install our testing equipment to aid in diagnostics. Next, I want to remove the bulbs. This step eliminates all engineered paths to ground. That way we have created an intentional open. We know there is a short, but this step will help us isolate it. Now what we are going to do is set up a test light to look for ground. We will begin by placing the test light's probe tip carefully into the output terminal of the fuse socket. We do not want to force this terminal open. Doing so will cause problems for future fuses. If the circuit was working properly, the light never would have illuminated. This confirms that we have an active short. Leaving the test light in place, we will now begin by opening parts of the circuit. We will start with the switch. If the light stays on, then the short was before the switch. Now you will have to move to a physical search of the wiring between the fuse and the switch, looking for evidence of recent repairs, vibration, heat, animal activity, or anything out of the ordinary that could cause damage to the wiring. If the switch being opened caused the light to go out, then we know the short would have to be after the switch. The next step would be to close the switch again and find another place to open the circuit beyond the switch. Since there is a terminal connector, it would make sense to unplug it to further isolate the next section of circuit. If after unplugging the connector the light stays on, this confirms that the short is between the switch and the connector. If after unplugging the connector the light were to go out, then we know the short is between the connector and the bulb sockets. Since we've confirmed the short is after the connector, then we need to now physically check the wiring like we did in the previous example, looking for evidence of recent repairs, vibration, heat, animal activity, or anything out of the ordinary that could cause damage to the wiring. One reliable trick to perform is the wire wiggle test after the connector. Remember, short circuits are an accident and not an engineered or built to last situation. If you can get the light to go out by gently wiggling a section of the wiring, so alternate between lifting and pulling in spots, then you just identified the area where the short is. Let's plug the connector back in and relight the test light. So let's perform the wire wiggle test on the upper bulb's branch. Since the light stayed on, let's move to the lower leg. Since the light continued to stay on, now let's perform the wire wiggle test on the section of wire connecting the two bulbs' sockets. The bulb has gone out because by wiggling the wire, we removed access to ground, thus identifying the area where the short was. So as we summarize electrical troubleshooting, remember for a device to work, it must have power and ground. If there is no power to a device, An open on the power side, like a blown fuse, is indicated. If there is power on both sides of a device, then it's probably an open on the ground side. If a fuse blows immediately, it's most likely a short circuit, which would indicate a grounded power side wire. So once again, determine and verify the customer's concern or verify the complaint. Perform a thorough visual inspection. Before diving too deeply into any diagnostic procedure, it's a good idea to check for technical service bulletins, TSBs, pull the wiring diagram, check any factory service information, and then use your procedures to determine the root cause. Once that's done, repair the vehicle and then verify your repair. This concludes the Part 2 lecture for Chapter 45, Wiring Schematics and Circuit Testing. For additional information on this topic, please read this chapter and refer to the PowerPoint found in the course content folder. Now that you have completed this lecture and you have written down the online lecture attendance codes, please go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture.